box is 12. It's 5 hours already, almost 5 hours. So. Okay? So you see that the structure is very similar to the previous one. Also the structure of the solution. So for instance, in the previous one, which was here, we had minus exponential minus x times basically a function of x here. And also in this case, the solution is minus constant times exponential minus ax times a linear function of x. So the structure is similar. So you can practice a little bit by changing the constants here. Also, you don't need to have a negative coefficient here. Also, in the case of a positive coefficient, you use integration by parts, okay? And it is even easier. So you can put, for instance, here 1/2 x times exponential of, I don't know, 1/4 x, compute, and check the result by computing the derivatives. This is a useful exercise. Okay. Another example of another very popular example of integration by parts is this one, the integral of the log of x dx. Okay, we know how to compute the derivative of the log. We know that the log is the result of the integral of 1 over x, but we don't know how to compute the integral of the log. Is there any function such that its derivative is equal to the log of x? It might seem strange, but this is computed by parts. Why? Because I can regard this as the product of 1 times the log of x. Okay? So I regard 1 as my g prime. Here there is actually no other possible choice. 1 is g prime, and the log of x is f. Okay? What is the derivative of 1? It is x. The integral of 1 is x. Okay? So a primitive of g prime, which is g, is x. Now I apply the rule of integration by parts. F times g, so log of x times x, minus the integral of g, which is my x, times f prime. F prime is 1 over x, the derivative of the log. I can simplify, and here I have 1. So the final result is x times the log of x minus the integral of 1, which is x. So the final result is x times the log of x minus x plus a constant. X times the log of x minus 1 plus a constant. Okay? Now, I want to show you one thing before solving another exercise, for instance, not on the log of x, but on the log of x plus 1, for instance, which is very similar, okay? So we wonder whether it is possible to compute by parts also this one. But now look at this example, which I already introduced before. What is the integral of x, let's say, plus 2 divided by x plus 1 dx? Here the integral is a simple ratio between two linear functions of x. Even very simple, the type x plus a constant, okay? And don't try to remember rules for the integral of the ratio, but just look at a way to express this as a sum of elementary functions for which you can compute the integral. So you can write this as x plus 1. In the denominator you have x plus 1. Unfortunately, here you have x plus 2, okay? Plus 1. So this is again x plus 2. Okay? But now I can split the ratio into two different functions. X plus 1 over x plus 1, which is basically 1, plus the integral of 1 over x plus 1. Dx, okay? So the result is x, because this is 1, plus the log of the modulus of x plus 1. Here, it should be divided by the coefficient of x, but it is 1. So this is the modulus of x plus 1. Now, remember that in many cases we can use this strategy. It is possible to use this strategy when we have the ratio between the linear function of x in the denominator and the linear function of x in the denominator. It's always possible to rearrange things in a way that you get basically a constant plus another constant divided by the same denominator of the initial ratio. Okay? It's always possible to do something similar. Now, look at this additional example. So how would you compute the integral of the log of 1 plus x dx? So we want to follow the same strategy basically, okay? So I want to regard this as the integral of 1 times the log of 1 plus x dx. Next, I remember the original rule. I regard this as g prime, and this as f. Okay? Next, I apply the integration by parts rule. So it is f times g, so x times the log of 1 plus x minus the integral of g x times f prime dx, okay, equal to x times the log of 1 plus x minus the integral of x over 1 plus x dx. Can we do here something similar to the previous example? Of course, I would like to have here 1 plus x, not x, okay? And then I have to write 1 plus x minus 1. So basically this one can be computed this way. The integral of x over 1 plus x dx can be regarded as the integral of x plus 1 minus 1. X plus 1 is 1, okay? So 1 minus 1 over 1 plus x dx, okay? Can check this. Same denominator, 1 plus x minus 1 becomes x. Okay, so this means that this is equal to x minus the log of 1 plus x. I should put the modulus here, of course, but in order not to complicate things, let's assume that this quantity is positive. So let me just show you how to, in many problems it is. So it's the log of 1 plus x, okay? So the final result is that our integral of the log of 1 plus x dx is equal to this one plus, minus, because there was a minus sign here, minus x plus the log of 1 plus x, okay? So there is a common factor between these two, so that could be rewritten as the log of 1 plus x times x plus 1 times x plus 1 This is not part of the log, of course. This is another factor, minus x. Okay? So basically, we can extend this structure also to other slightly more complicated structures. Okay, so I suggest that we stop for, let's say, 15 minutes now, 10 to 15 minutes now, and then we continue later. Okay, we're going to take a break, 15 minutes break now. Okay, so let me start again. You hear me? Okay. And of course, there was here in the last step of the solution, there was a wrong sign. Because here the factor was -6 exponential -1/3 x, so -6. So there should be a plus sign, not a minus, of course. Thanks to you for letting me know that there was a mistake. Now, this is maybe the last exercise. This is the last exercise. Now, what about different situations in which we have products or ratios between functions, but we don't have to apply integration by parts because it doesn't work or it is not convenient. Okay, so this is one typical example. Here I have the product between two functions, but it's not useful to apply integration by parts. Okay, what we have to understand these structures is that here we have a composite, we have the exponential of the function of x, this example, times something that can be easily used to the derivative of this function of x at this point. If you look at the structure here, you see that exponential of -3x plus 5, the derivative of the exponent would be -6x. Here we have 2x, but the important thing is that we have x here, and you can adjust this factor by just working with multiplicative constant. So we can take -6x here. To do that, we multiply this by -3. We have also to divide by -3. Okay. Now look at this structure. The integrand now is something like the exponential of f of x times f prime of x. So it has this structure. Okay. It has this structure. So basically, this is the typical structure of the derivative of the application chain rule. This is the derivative of a composite function. Okay? It's not f of x, it's exponential of f of x. If I take the derivative of this, the derivative is exponential of f of x times f prime of x. So in the integrand, we have the structure of the result of the application of a chain rule. This is the main message. And this happens sometimes we have products between functions. If we can reduce it in this equation, then we can immediately write the result is -1/3 times the exponential of -3x squared plus 5. Okay. Of course, this is just an example, but this is not the only situation that can happen. You may have many different situations. For instance, this one, when we have an integrand that can be reduced to this expression, f prime of x over f of x. This is clearly the derivative of the log of f of x as a constant by applying the chain rule. Okay, the log of f of x becomes 1 over f of x times f prime of x. Okay, this is another possible situation in which we have the structure of the derivative of a composite function in the integrand. Of course, as a minimum, we have to adjust the multiplicative constant in order to find, to highlight the right structure in the integrand. Okay. What about this case? F of x, f of x squared. We have some function squared in the denominator multiplied by its derivative. This is a typical case of the derivative of the power of some function f of x. Okay. It is f of x to the power of -1. So the integral of this is -1 over f of x plus c. Because if you take the derivative of this, you get it is minus f of x to the power of -1. So if you compute the derivative, it becomes minus -1 f of x to the power of -2 times f prime of x. So apart from the sign here, you have basically this, the derivative of this function. Okay, you do have the derivative of this function, but if you consider the derivative of f of x to the power of -1, that would be minus this. So try to see if you can identify structures in the integral by which, apart from the multiplicative constant, you have the result of a chain on the side. Okay. So here are just a few examples. For instance, this one. Suppose that you have this. The integral of 5x divided by 3x squared minus 2 squared. So in the denominator, I have the square, so power basically, of a function of x. The derivative of this function of x would be 6x. In the denominator, I have 5x. I can obtain 6x by dividing by 6 as well. Okay. In this form, integral is something. The integral is something which is already displayed here. The derivative of -1 over 3x squared minus 2. So the result is 5 over 6 times 1 over 2 minus 3x squared plus c. Of course, you need some exercise, some practice to identify these structures in the functions. What we can do basically is this. If you want to practice with this kind of exercises, to get used to recognize the structures into the integral, you can just do like this. For instance, a power function, for instance, 3 1 minus 3x squared to the power of -1/2, and compute the derivative. Sorry, to the power of 1/2, for instance. Compute the derivative. So the derivative of this would be 1/2 times 1 minus 3x squared to the power of -1/2, okay, times 6x. Now try to, so it's basically given by this, a power function of a function of x times basically a constant times x, okay? So you can just start with another function, for instance, 1 minus 3x squared times, for instance, minus 3x. And try to compute the integral of this one. Okay? So So you change you compute a derivative of a composite function apart from, and you change basically the constant, and then you try to go back, try to obtain, to rearrange this in a way to have here the derivative of the argument of the square root in the denominator. And if you do that, you adjust for constants inside and outside the integral. You can obtain inside the integral a function that has a precise which is the derivative of another function by applying the chain rule. Okay, so in this case we should have here minus 6x. We have minus 3x. Okay, so it is 1/2 times the integral of minus 6x over 1 minus 3x squared dx. This is exactly the derivative of square root of 1 minus 3x squared, okay? So we have 1/2 square root of 1 minus 3x squared plus c, if I'm not wrong, okay? So basically you can just take a power function of some function of x and multiply it by the derivative of this function, possibly with a different multiplicative constant, and then try to compute the integral of this function, okay? And then check the result by computing again a derivative. So basically, we need a little bit of practice. Another example is this one. Look at this one. This is very useful also to think of the meaning of. I think a bit about the meaning of multiplicative constant in the solution. Suppose that you have this function, you want to put the integral of this function. Okay, we look at the structure, we see the function in the denominator. And we wonder whether the denominator is the derivative of the denominator, because in this case we would have a structure of the type f prime over f. Okay, and the integral of this is the log of f. Now look at this. The derivative would be 10 plus 4x. Here we have just 5 plus 2x. Okay. We basically have the derivative here because the derivative is this one by 2. Okay, alternatively, we could regard the denominator as 2 times 5x plus x squared. In this case, we could move this 2 outside the integral in the denominator, and we would have 5x plus x squared in the denominator and 2x plus 5 in the denominator, which is precisely the derivative of this. Okay? So let's follow this strategy first and then the other one. So let's start from this one. I regard the denominator as 2 times 5x plus x squared. This way, if I get rid of this 2 by moving it outside, okay, in the denominator I have exactly the derivative of the denominator, okay? So basically, the result is 1/2 times the log of 5x plus x squared plus c, okay? So this is my result, assuming of course that 5x plus x squared is strictly positive quantity. Otherwise I should do here a modulus sign. Suppose that you don't follow this strategy and you follow another strategy. You don't modify the function in the denominator. You look at the denominator and you see that this is, if you multiply this by 2, you get the derivative of the denominator. Okay? So basically, you would like to have in the denominator 4x plus 10, but you don't have it. Okay? So you have to multiply by 2 the denominator, and of course to divide by 2 outside. Now we have a function in the denominator and its derivative in the denominator. Okay, this is the log of the denominator. So 1/2 times the log of 10x plus 2x squared plus c. This is correct? This is correct. But this is not the same. How is it possible? Of course, everything, the reason of this is that this is an arbitrary constant. This is an arbitrary constant. We call them C in both cases, but this is basically different from this one, okay? This is an arbitrary constant, but not the same constant in the two cases. Why is that? Because if you can write this solution as the log of 2 times 5x plus x squared plus c. This, by a property of the logs, this is the log of 2 plus the log of 5x plus x squared. So you have here 1/2 log of 2, which is a constant, plus c, plus 1/2 the log of 5x plus x squared, which corresponds to the previous solution. So you basically have here the same quantity plus another constant that we call c prime. Since our constant is arbitrary, it's clear that this solution is the same as this one. So I want to point out, this is not wrong, this is correct as this one. In some cases, the fact that the constant is arbitrary may give rise to a seemingly different expression of the solution, okay? But remember, especially in logs, but remember that the constant is arbitrary. So this captures the whole set of solutions exactly as this one. Okay. Now, look at this other problem. I'm trying to solve it here. Look at this one first, and then another more difficult of the same type. This is an exercise in which we have to find the set of functions, not the set of functions having a given derivative, but to select one specific function among this set of functions having a given derivative. To do that, we have to impose an additional condition. Select one among the infinitely many solutions. We have to fix another additional condition, which is called in general boundary condition. Okay, it's called boundary condition. The problem could be like this: find a function f, capital F, having this derivative, and passing through the point 1, 2 in the plane. Okay. If we add this additional condition, which is called, this is one type of boundary condition. From this one, we have family of infinitely many functions, but adding this, we can select one among these functions, okay? Only one. What is the solution to our problem? It is x squared plus a constant. This is a family of parabolas, like this. Okay? X squared plus c, c is a real number, and c represents the vertical coordinate of the intersection point, the vertical axis of the symmetric parabola, okay? This symmetric with respect to the y-axis. Infinitely many values of c, infinitely many parabolas. Among them, I want to select the one passing through point 1, 2. Graphically, it is the right one. Okay? How can I do that? I want that parabola passes through point 1, 2, so f of 1 must be equal to 2, where f is capital F. Okay? It is the solution to my integral. F of 1 is 1 plus c, and this is equal to 2, and this means that c must be equal to 1. Okay? So selecting one parabola among the infinity many means finding a particular value of c. Okay? And in general, when we have this kind of boundary condition, we identify only one, a unique function among the infinitely many functions that solve our integral. So our function is f(x) equal to x squared plus 1, okay? Which is precisely this. Passes through point 1, 2, and it has the expression x squared plus 1 because the intercept, let's say, is at point 1. This is an example of application of a boundary condition. Of course, these kind of boundary conditions are very popular and very common in the solution of differential equations, which is another type of integration. Okay? So another example similar to this one could be this one. Find function f, capital F, having this derivative lowercase f of x is equal to 3 minus exponential minus 0.05 x, and passing through point 0, 10. Okay? So first of all, we have to find the family of functions having this as a derivative and to express times x. Of course, this can be written as 3 minus exponential of minus 1 over 20 times x. Okay? So the integral minus 20 times exponential of minus 0.05x, okay? Plus a constant, so equal to 3x plus 20 times exponential minus 0.05 x plus a constant. I want that f of 0 is equal to 10. Okay? So f of 0 is 3 times 0, which is 0, plus 20 times 1. Which is 20. Sorry, plus c, of course. I forgot the c, the most important thing. C, which is 20 plus c, must be equal to 10, okay? So c is equal to 10. So my solution is, I can indicate my specific solution this way, my particular solution in this way, is f of x equal to 3x plus 20 exponential minus 0.05 x plus 10. Okay? So this is an example of application of a boundary condition, and in general, the application of a boundary condition, sorry, C is minus 10, of course. C is minus 10, so this is minus 10. Please stop me. This is minus 10, of course. So this is an example of application of a boundary condition, okay? Boundary condition means, Italian is condizione al contorno. Boundary condition means that I'm interested in computing, not just computing the family of solutions, but among them, a solution satisfying a particular additional condition, which is called in general boundary condition. In differential equations, the type of boundary condition which is very popular is the so-called initial condition. Okay? So typically, I have a differential equation which relates the instantaneous change of a given quantity to the level already reached by this quantity. And by this relation between instantaneous change and the level, I can integrate and derive the family of solutions. But then I'm only interested in the particular solution that starts, for instance, from the level 100 at time 0. This is an example of initial condition. It is a type of boundary condition among the infinitely many functions, trajectories that express the solution, which is the kind of indefinite integral. I can set one specific which is interesting for my problem. Okay. Another popular type of conditions in dynamic optimization is a so-called terminal condition. Okay, I want to end up with a given level of my variable. I'm not interested in the initial level, but I want to end up with a given terminal level of my variable. This is called terminal condition, but they are all types of boundary conditions. Okay, so that allow to select to obtain just one solution from your problem. So this is another example of. I could leave you as an exercise. This one. I want to stop a few minutes earlier today. I hope you don't mind. Okay, this is an exercise, but it is very instructive. They are two, actually. One is computing the integral of x times the square root of x plus 1 dx. And one is computing this very similar integral, which is x times the square root of x squared plus 1 dx. They are the integrals of product of two simple functions. Each of them has this structure, but the techniques to solve them are really different from one another. Okay, so here we exploit the technique of recognizing here the derivative of a composite function. Okay. So reduce it to the structure of derivative of a composite function. So the result of the application of the chain rule, okay? And here, which is slightly more difficult, but not, it's relatively easy. You cannot do that, and you can integrate this by parts. Okay, so I invite you to. This is very similar to the exercises we solved already here today. This is a little more difficult. But of course, you can check the results at the end, so you can just compute the derivative of your result and obtain again the integral, okay? So I invite you to solve these two exercises. Here, an interesting point here, what is better to select as F or as G prime, okay? Because in principle, you don't know that. You could select this as F, this as G prime, or this as G prime, and this as F. Okay? Try to solve it. Okay? You can check the result by yourself at the end by computing the derivative. Okay, I think that we can stop here for today. And next time I will introduce, tomorrow basically, I will show you the solution to this. Maybe next week, because I'm not sure that you are going to solve it tonight, so maybe next week I will give you the solution to this. And Tomorrow I will start with basically the definite integral. The definite integral, because it is much more important for our application to differential equations. Okay, thank you, bye.
Thank you.
See you tomorrow morning at